Our first example of applying the Noether isomorphism theorem will be to look at an example we saw previously. So we look at the principal ideal generated by X in Z adjoin X, and we want to know sort of what is Z adjoin X mod X as a ring. And I'm going to give you a couple of ways of thinking about this. So firstly, X is the collection of polynomials without constant term. That's what we decided in a previous video in the previous section. Or if you like, it's like explicitly x p of x, where p of x is an integral polynomial. And we saw that congruence mod x earlier in this chapter, or this section, is, well, is asking if they're congruent is basically seeing if the constant term for each polynomial are the same or not. So is comparing constant terms. Namely, we saw that p of x plus x is q of x plus the ideal generated by x, if and only if the constant term for p is the constant term for q. So we saw this already. I'm not going to rehash it. Okay, so what this is saying is somehow like all of the x's don't really matter in p and q. The only thing that matters is the integer that represents the constant term. So what this is telling us is we might suspect that z adjoin mod x, z adjoin x mod x is just z, because somehow only the constant term matters, and we have z many constant terms. And in fact, this is true, and we're going to prove it. You can prove it just directly with playing with cosets. This is actually one of the easy ones that you can do just with the definition. Once you know that when you mod out by an ideal, you get a ring. We are not going to do that though. So you can do this without, you can do this sort of directly without the isomorphism theorem that we proved. But we're not going to. So what we're going to do is we're going to appeal to the isomorphism theorem now that we kind of have a guess as to what the right thing should be. So to apply the Noether isomorphism theorem, we need a homomorphism. So let's consider a homomorphism. And before I say what it is, it needs to go from z adjoin x to z, and it needs to have the ideal generated by x as its kernel. Well, we had a homomorphism a while ago. It was evaluation at 0. And this guy had exactly this ideal, this ideal as its kernel. So we're going to consider this homomorphism. Why is it a homomorphism? Well, we proved evaluation maps are homomorphisms, so I'm not going to rehash that. And just to remind you what it does, it's going to take a polynomial, so p of x, and it's going to plug in 0. Or said differently, if we were to write p of x out as some a0 plus a1x plus a and x to the n, evaluation at 0 of p of x is plug in x equals 0. If we plug in x equals 0, you just get a naught. Okay, so that's what it does. And as we can see here, the kernel of this map is exactly those guys where there is no constant term. 0 constant term. Because those are the guys that are going to go to 0. All right, so it's a homomorphism, check. The kernel is precisely the ones that have zero constant term. That's precisely the ideal generated by X. Check. It's actually onto, oh, sorry, oops. By phi, I mean evaluation at 0. My bad. Just did all the Noether isomorphism videos and I'm in the phi mode. Sorry, an evaluation at 0 is an epimorphism because if you were to evaluate at 0 your favorite constant polynomial, I don't know, let's call it A, you get A. So if you have any A in Z, look at the constant polynomial A, that will evaluate to A. So it's onto. Okay, so by the Noether isomorphism theorem, we learn that Z adjoint X mod the kernel, which is the ideal generated by X, is isomorphic to the image, but it's onto. And the image, therefore, is just all of Z. It's all the codomain. And furthermore, the Noether isomorphism theorem isn't like an abstract, oh, these guys are the same. We actually know how to show they're the same. So if you have some p of x plus x here, where p of x you can imagine as writing like a0 plus a1x plus so on, that's going to go to a0. It's like you take your coset representative, you look at its constant term, you pick out the constant term. So the isomorphism is not inexplicit, it's very explicit. So let me just say given by that function, which is great. Explicit things are great. And so this is our first example of identifying a quotient ring using the Noether isomorphism theorem.